Hello everyone, I am Markus Tavenrath, Principal Engineer Developer Technology at NVIDIA, working on deploying AI. So this is slightly more practical because today I want to talk not about AI models, but how do we bring those AI models to the actual hardware, to the engine for those models so that you can do something and not just have theories. And so first, let's talk about who is Khronos. Khronos is a non-profit standards consortium focusing on creating royalty-free standards. And Khronos was founded in the year 2000. So we are 25 years old now, yay. And initially we started working on acceleration APIs for 3D, but extended to file formats, extended reality, vision, parallel compute, and most learning AI. And the membership to Khronos is open to any organization. So within Khronos, I got ML Council Chair a while ago, and when I started to bring up this group, we had this nice diagram for the machine learning acceleration ecosystem. On the left side, you see open source frameworks like TensorFlow, PyTorch, Llama's AP, Paddle. On the right side, there are acceleration APIs and SDKs. Why do I say SDKs for acceleration APIs? Because there are some parts within the ecosystem, especially for NPU, where there is no open standard available at all to access an NPU. Each and every IHV today has their own proprietary neural network acceleration API or SDK, which is a mixture of a compiler runtime and library, which is why some of those SDKs are not just on the right side, but also in the center, which is mostly driving the ecosystem, compilers, runtimes, and libraries. And so the arrows are for direct integrations of those compilers, runtimes, and libraries into the frameworks. And it's a total chaos. If you would be an ISV and you would want to start today writing a new software and you want to deploy an AI on a desktop, where do you start? Which framework do you use? Which compilers and runtimes does the framework need? You have to deploy everything. You have to figure out the licenses. Some of the frameworks you have to compile by your own. So you have to find the correct libraries, get all of them always synchronized. You have to update those. And then you have to decide, what is my target market? And depending on the target market, you have to set the compile flags and ship those libraries with your application for your target market. But what if some of your customers come and have a new device and you didn't compile for the new device? It won't be supported. And if some vendor comes with a new API, imagine about all the software cycles. On day one, the SDK is released, and you missed the release date of TensorFlow or PyTorch by 1 day. So you will have to wait for the next release of PyTorch to get somewhere. And then you have to release your application again. And if the next release of PyTorch was also 1 day late after your next application release, then you missed 2 cycles in the software ecosystem to get your neural network engine deployed. So the whole ecosystem is super complex and adds a lot of problems to everyone in the ecosystem. So within Khronos, we decided we start an ML market research. We really want to try to figure out what is happening. And we interviewed a lot of key decision makers one-to-one across the entire machine learning stack. We asked AI model experts, platform developers, hardware vendors, AI compilers, tool vendors, and standards organization bodies, with the goal to understand what are real-world machine learning acceleration pain points they are developing, so they're facing. And how can standard bodies like Khronos help to reduce this ML ecosystem complexity so that we have less different frameworks to support or compilers. And the key result from this market research was one common problem. If you want to launch an AI product or any AI feature, you need a lot of manual expert work. Up to 85% of ML deployment efforts in your applications are related to manual expert work, meaning you need to hire experts taking care of optimizing and developing the backends required to run your machine learning. And only 50% goes to other tasks. And we all know that it's really hard to get machine learning experts these days. So let's take a closer look why we need so many experts. So on the left side, we have machine learning frameworks, and there are many frameworks. In the center, we have the compilers, runtimes, libraries, and all of those are seeking optimal acceleration. And the reason why there's so many is that everyone tries something else and wants to compete. And on the right side, we have acceleration APIs and SDKs, depending on whether you want to support a specific NPU or something more generic like Vulkan or OpenCL. And we have a huge combinatoric explosion of potential combinations. And so if you are an IHV, and you have a hardware SDK, you have to provide this hardware SDK. It has to go into compilers, runtimes, libraries, and then it is into frameworks. It will take a lot of time for you as IHV to ensure that your SDK is being integrated in the whole software stack. And every time you are releasing a new version of the SDK, it is your responsibility to go to those frameworks and tell them, I have a new version, can you please update it? For the framework developers, it's even worse, because they have no dependencies on all your libraries and SDKs. And if they want to change something in the framework, the more different libraries they have, the more burden they have to bring changes to this framework, because they have to change all the interface to all the SDKs. If you're the ISV, you have to do all the testing on all the SDKs you're shipping within a single framework. This means you have a slow adoption of new hardware features, because most likely you're going to limit the release frequency, updating SDKs, or you're not supporting all the hardware there. So it's causing a really fragmented platform support. On the other hand, we have a lack of performance portability. Speed of light performance is the maximum achievable performance you have on a specific hardware. And you want to get speed of light to be energy efficient and competitive, because if you buy a $100 chip and you can get only 10% speed of light, you are wasting $90 of a $100 chip. So then if you would have a $10 chip and you would achieve 100% speed of light, which is not realistic, you would have the same performance at 1/10 of the price. So you really want to have speed of light performance. But since every acceleration API might have a different operator set, or might lack some operators, you would have to write custom operators. Or certain operators are faster than others depending on the SDK. You have to take care of graph rewriting and scheduling all of those, taking a lot of manual expertise, a lot of time of porting and verifying that all your assumptions are still true. And all of this is really slowing innovation across those frameworks, or bringing new model architectures to the market. If you have a new model architecture, those frameworks will have to ensure that new operators somehow get integrated into all those acceleration APIs. It's a lot of duplicated efforts across the experts we could avoid if we would have a common acceleration API. And the worst thing of everything, we are doing this to support end users. End users want to buy our hardware, our software. But by having this fragmented ecosystem, if a user buys a hardware, there's sometimes not a guarantee that the software will even run, depending on which SDK is being used. So the question we have is, can open interoperability standards help with all those problems? And yes, open cross-vendor APIs benefit the software and the hardware vendors, and in the end, even the end users. As software vendor, you have reduced costs deploying your software, because you don't have to think about so many different SDKs, you don't have to roll out testing, so you save on cost for testing, and people run the tests and evaluate the tests. Also, you have a way broader market reach. You don't have to think about, okay, which IHV am I going to support? AMD, NVIDIA, Intel. Maybe Qualcomm is on the desktop as well. Do I want to support them, or is 3%, 5%, 10% market share not enough? this shouldn't be a thought of a software developer. It should be, I want to run on Windows, I want to run on Linux, and it should just work. For the hardware vendors, if you would have an implementation for an open cross-vendor API for machine learning, then you have access to a very broader software ecosystem. As soon as you have implemented this API, your hardware will run with every framework supporting this API. You wouldn't have to release a new SDK and maybe certify the SDK for safety that it can be used in a car. You would have an API which will be safety critical, and then you, of course, have to validate your API against it, but it's way less work. And so we really need a robust API design and support and input from multiple companies to get there. On the other hand, we have to figure out what is a good time to define an acceleration standard. Because if we would be too soon, then it's possible that the standard requirements might change a lot, and then we would have to redefine the standard. But if we think AI is starting to get in a place where it's proven and stable, or mostly proven and stable, then we can start today. And since there will always be changes, the standard would also have to be extensible so that we can accommodate technology changes. If we would define a fixed standard which can't be extended, we are reinventing standards all over time and make it even worse in the ecosystem. So, what could hardware vendors do for ML? In general, the industry thinks that sophisticated lowering ML compilers, and with lowering ML compilers, I mean compilers taking a machine learning graph and compile it down to compute kernels with potentially one compute kernel per operator, or even by fusing multiple operations into a single kernel, is the road to solve performance portability. But there are backend issues that are not great. Those compiler stacks define custom operators to try to gain access to efficient operations. But if you have this operator proliferation and you would go to compute kernels and you have different compute APIs in the backend, you have to generate those compute kernels for each hardware vendor to be efficient and run at speed of light. And if you would be an NPU vendor and you would integrate into such a pipeline, you would lower only 2 operator sets. But you would have to add support for all the new operator sets all over again. And if you can't deploy those operators fast enough, then your hardware will get outdated really quick. And the other problem is the current open standard intermediate representations, at least those for compute, don't carry operator graph information. If you are in compute, the IR contains information for a single compute kernel and maybe a few functions which can be called. But the driver does not have information, this graph, this operator, or this kernel is dependent on another kernel or operator dependent on another one. So the amount of device driver optimization is limited to a single kernel only. There's no global graph optimization available. And as soon as the graph had been lowered to compute, it cannot be applied to NPUs anymore because NPUs most likely have a way more limited programming model or even fixed hardware. So what we really need is a effective cross-planet standard for machine learning acceleration to reduce the number of needed backends. And can we create a cross-platform standard that addresses the pain points we have identified? So that we don't have too many different operators, that we can have a graph in an IR, and this way even solve the NPU deployment pain points, having one SDK for each NPU vendor at least. And with that in mind, let's take a look at what Khronos is currently doing for the standards to accelerate machine learning. So initially, machine learning went through compute shaders on each and every hardware before NPUs became a thing. And currently, many of the machine learning workloads are dominated by matrix-matrix multiplies, matrix-vector multiplies, or convolutions, which also can be expressed as matrix-matrix multiplies. And for those operations, there are 2 different performance bottlenecks we have to address. It's memory capacity, meaning the size of memory and the bandwidth, and compute throughput. For memory capacity, there's only so much amount of memory we can attach to a chip, because the maximum chip size you can buy, and then the number of pins your GPU can connect to the chips. But there's also a limitation on the amount of memory bandwidth for each pin you can achieve. And if you would have a matrix vector multiply limited model, most likely memory bandwidth will be a bottleneck. And you can even compute the speed of light performance of these models by just dividing your model size by the bandwidth you have on your system. And the only solution to be faster here is to quantize the data. So we want to reduce the bit precision for each weight. And in Vulkan, we added data types for the typical machine learning quantized formats, like int8, int16, float8, float16, and bfloat16. And by introducing those types, we can reduce the size of the weights to be loaded from memory and to be computed by 2 to 4x. And this means we can run the network 2 or 4x faster if memory bandwidth was the issue before. On the other hand, we also can load a 2 to 4 times larger model onto the GPU if we need larger models. On the other hand, we have compute throughput. On a chip, the number of instructions per clock is limited, the maximum clock is limited. We can't just ramp it up wherever we want to do. So the way to go is parallel operations. We want to execute more operations with a single instruction. And the solution to this is cooperative matrix operations. The idea is that a single group of threads operates on highly optimized parallel matrix multiplies. This way, less data has to be pushed into the chip. We have more mass for each instruction. And, well, you can get a 4x plus speed increase. We have seen 7, 8x even on GGML by using those extensions. And this gives you a pretty good speed up with those Vulkan extensions on machine learning. And looking at Llama CPP GGML, we have seen that the Vulkan backend on NVIDIA hardware is competitive to the CUDA backend in certain models. Sometimes it's slower, sometimes it's faster, but we are quite close. And the Vulkan and also OpenCL are continuing to expand these data types and intrinsic operations to speed up ML operations for compute GPUs. And with those extensions, Khronos APIs have been widely adopted by a lot of different frameworks. Traditional OpenCL was the compute backend in Khronos, and so it has a wide support across many different frameworks, compilers, SDKs. Some of them are for a single vendor only, unfortunately. But Vulkan is, with those new extensions, now becoming increasingly used across all markets, including GGML Llama CPP, which now has a good Vulkan backend. And the base for everything within Khronos, so the IR is SPIR-V. So we need an IR, or we want to have a common IR for all compute APIs within Khronos. And so SPIR-V was developed a few years ago, and it's being used by Vulkan, OpenCL, and SYCL. And SPIR-V is designed to support graphics and compute cases at the same time. It is a simple binary format, easy to parse, easy and fast to parse and to analyze, and most importantly, it decouples compute and the shading language from the API. In the past with OpenGL, you had to pass in GLSL shaders to the driver had to parse, and different implementations had different parsers with different results, which made it hard for ISVs. With SPIR-V, you can pick and choose the compiler you want to generate your SPIR-V code. So you can go with a traditional GLSL using GLSlang. Quite famous among game developers is the DirectX shader compiler DXC, which can generate SPIR-V now. In LLVM 20, they have introduced an official SPIR-V backend. And Slang, of course, Khronos' shading language and compiler, supports SPIR-V. And MLIR, as machine learning intermediate representation and compiler framework, also has support for SPIR-V. And so with SPIR-V being the central part, it can be consumed by Vulkan, SYCL, OpenCL, and by a tool called SPIR-V Cross, also by Metal, and it can generate HSL and GLSL. And quite new, Microsoft announced that they adopted SPIR-V for their DirectX shader model 7. So SPIR-V is now widely accepted within the industry and the compiler frameworks, and quite important, it's easily extendable to add new features, which makes it so great. Vulkan and OpenCL are designed to be extensible so that hardware vendors can innovate and propose new features, which then get adopted by more and more hardware vendors if the software developers want to have those. And yeah, this gives the industry a way to adopt those new features. Also, SPIR-V is forward compatible. So LLVM had the problem that if you upgraded your compiler, you needed to upgrade every software which consumes the output of the compiler to a new bitcode version, which is not realistic for a driver. If you update your compiler, you do not want to update your driver as well. There's no guarantee that drivers get updated. And finally, for SPIR-V, we have a quite extensive open source tooling so that we can read, write, validate, and transform SPIR-V between different representations. With SPIR-V as intermediate IR, the next question was, can we bring graphs and tensors to SPIR-V? And ARM did a great job bringing, defining extensions, currently vendor specific, to add a graph and tensor support to SPIR-V. And while ARM proposes TOSA as the initial operator set, they designs extensions in a way that TOSA is not the only operator set which can be designed. It is extensible to any operator set you want to have inside. Unfortunately, there is no custom support at the moment in this extension, meaning you are limited to the operator sets which are being defined. And with SPIR-V supporting graphs, the complete neural network can be sent to the driver as a single SPIR-V blob. And now the driver has the full information for graph optimization. So it can choose optimal kernels instead of relying on SDKs to optimize the optimal kernels. It can use information which is not made public through the API yet. The hardware knows things like cache sizes, so it can choose tiling instead of running each operation in the graph one next to each other. And most importantly, since we have high-level information about operators to execute, with this extension, we can support NPUs within Vulkan. As long as the NPU supports the operator set, you can make a driver for your NPU running Vulkan to support those graphs. This leaves the question, how would we want to handle custom operators in the SPIR-V graph now that we can run the graph in the best possible way within Vulkan? And we are currently seeking industry feedback what the custom operator requirements are. Our research says 20 to 30% of the typical pipeline operators are custom operators. But we don't have information how those custom nodes are distributed in the graph. We assume that it's possible that it's pre- and post-processing, meaning you are running some custom operations to bring the data in a format that the graph requires. You execute the graph, and then you get a result, and then you have to do processing. If custom operator requirements are just this use case, we are good with the extension we have as it is today, because we would have to synchronize 2 times. It's not critical in the total pipeline execution time. But if someone would want to do every second node as custom graph, then this solution would not work, because the synchronization overhead by splitting the graph into compute and non-compute would be way too big. So what we as Khronos are really interested in, what kind of programming model would you expect from compute kernels in the graph? We have one idea of a programming model we want to propose, and we want to validate if this is useful for you as well. NNEF is going to be released soon in a second version, and NNEF itself is a Khronos open standard file format for describing neural networks. It has 2 key aspects, the neural structure and the network data. The network data itself is not critical, it's just consumed by the GPU, but the neural structure is a focus for today. Traditionally, neural network exchange format like ONNX defined a fixed operator set. And the documentation, what an operator is doing, is written as text. And if you would want to implement a backend supporting ONNX, you would have to read the documentation and try to make your best writing the code, which can be quite time-consuming. NNEF by itself defines a SkriptND domain-specific language, which can define shape inference, one-time computation of tensor operators called primitives. You can generate compounds using primitives or other compounds, control flow constructs. It has branching, looping for dynamic models, and of course you can define the full neural network graph consisting of premises and compounds. And because SkriptND defines the operators through a scripting language, a network defined with SkriptND is fully self-contained. If you would have a programmable execution engine below the compiler, like a GPU or CPU, or a flexible NPU with a simplified programming model, then a single SkriptD model would give you everything you need. And if there's a custom operator, it would be defined in SkriptND and just compile. And for an implementer, well, there are two ways to handle those. First, you can handle the tensor primitives through an optimized path, meaning you know a primitive, you map it to a specialized hardware unit or compute kernel, and everything is good, or you go fallback path and compile the SkriptND into some compute shader. If you have compounds like a convolution followed by batch norm, followed by ReLU, if you know this fused operator, you just provide it and use it. If you don't know it, the fallback path would be that the front end of NNEF would just lower the compound, breaking it down, and then repeats, checking for primitives you are supporting. And this way, an implementer can choose which primitives and computes to optimize and which ones just to let to be handled by the compiler. And this gives a guaranteed forward compatibility. New primitives will always have a compiler fallback to run on programmable hardware. And this way, models will always run. Here's a small example I just want to show, showing how simple a SkriptND looks like. So it's an einsum-like notation, completely independent of any hardware details. Basically, for each output, you have a computation formula you have to define. You don't need to care for shared memory, register allocations, warp size, anything. And defining the graph is also extremely simple, human readable. We are interested in if you like this kind of description and would want to see it. We also have extensive tooling in GitHub for network conversion from ONNX, TensorFlow, TF-Lite. We have exporters to ONNX and TensorFlow. And for network execution, there's a small C++ code generator. We have a parser, front-end, runtime, and even a TVM-based sample compiler, which can compile to Vulkan, CUDA, and CPU code. And if you're interested, check out the QR codes, give it a try, give us feedback. And the final question we have to the industry is, if you think SkriptND is a great thing, should we embed SkriptND or the concept of SkriptND into SPIR-V graphs, so that you have a single unified way to pass compute and the graphs to your hardware? And for adoption, should we try to drive an industry-driven open source project where the SkriptND compiler would first compile to compute, but would also be able to have support for machine learning intrinsics, the graph, and in the final version, have a full SPIR-V support with SkriptND in the driver? Should Khronos initiate such an open source project to enable incremental industry rollout of SkriptND-based operators? So Khronos really proposes the industry backend acceleration of ML stocks. And should we do SPIR-V graphs? Should we do SkriptND for the operator programming? And should we continue innovating on compute shaders to define a simplifying cross-platform machine learning acceleration? Thank you for your time.